Last time on Wince versus CERN.
An Italian professor who thought he'd disproved Einstein's theory of relativity has resigned after it turned out he hadn't.
But wait, is that really how it played out? Despite the fact that Opera itself never claimed to overturn Einstein's theory, many newspapers depicted it that way. Although technical issues seem to have been the cause of the speedy neutrino results, physicists' excitement was unfairly translated into "Einstein was wrong" headlines. Both Opera and its sister experiment Icarus are scheduled to rerun the neutrino experiment at the end of this month, though most experts expect the particles to obey the speed limit this time.
Something is seriously wrong with this picture. There is a hidden negative sign in this equation below, a cover-up, something they didn't want you to see. A fact revealing what is actually wrong with this data. While they were doing this test with the Opera detector, they also had another detector running, which was called the Icarus detector. If you look here, you'll notice that the dotted line is slightly to the right of 0, which would indicate that this is a positive number. What the reality is this equation was gauged. They actually had to hide a negative sign in the equation so that the answers would always come out positive. So for all objects that travel slower than the speed of light, this value is always going to be larger than this value, which means this will always be a negative number. So the fact that the equation was set up to not give a negative number means that the scientists at CERN know there's a problem with the mathematics. This actually brings us right back to the issue regarding the time of flight equation.
The only objects that can travel at the speed of light are massless things like light.
According to modern physics, the neutrino has mass, which means that no matter what, theoretically, not only are neutrinos forbidden from traveling faster than the speed of light, but they are also equally forbidden from traveling the speed of light. It is as if everyone was so concerned about negating the superluminal Opera results that the subtle anomaly with Icarus went unnoticed. Therefore, we must wait for the May results. I guess we are just going to have to wait. So, while we wait... Oh wait, just a couple days after I uploaded my YouTube video, looks like we've got some results. I guess it's time for an encore presentation. Shall we? Is about to start. Who will win? Okay, so the neutrino time of flight wasn't 60 nanoseconds faster than that of light. But it was 6.5 nanoseconds faster, on average of course. So, if I remove approximately 1 order of magnitude from what I demonstrated in April, then this particular application of existics to physics still applies. The real issue here, which I raised long before the June 8, 2012 publication by CERN, is still glaring right at us, right there in plain sight. There is an extra aspect of the neutrino time of flight not being properly accounted for. As part of my publication prediction and announcement April 17th, 2012, the Icarus results were just as problematic as the Opera results, reflected in the mathematics used to derive the time of flight of the neutrino in comparison with light. The real issue, obscured by the media hype surrounding the controversial Opera results of 2011, was that the Icarus results were consistent with the Minos results of 2007, where the neutrino began to exhibit slightly superluminal speed. If we remove the entire Opera ordeal from the data, the problem remains the same. why does the neutrino appear to travel slightly faster than light on average, though we know it doesn't? Opera's loose wire debacle was really a red herring, obscuring the fact that relativity in its current form cannot completely deal with the neutrino velocity data without a little mathematical hand-waving in the end. Whether we like it or not, the data from the main analysis shows that the mean average is slightly superluminal, statistically speaking. But that's the irony. Physicists are making a worse claim, stating the data fits within predictability of relativity, that is, within statistical error. Seriously, which makes more sense? Focusing on the average, the mean, or the margin of error? Imagine safety standards based on margin of error.
This vehicle's safety has an average rating of slightly unsafe, but its safety rating falls within the margin of error of safety standards, so it's safe.
Would you want to drive that car? So why would we apply the same reasoning to our understanding of the universe? The apparent question becomes obvious. Do we need a theoretical adjustment or what?
The essential achievement of general relativity, namely to overcome rigid space, is only indirectly connected with the introduction of a Riemannian metric. The directly relevant conceptual element is the displacement field, which expresses the infinitesimal displacement of vectors. This makes it possible to dispense with rigid space.
So let's take a scroll through the actual data and see which interpretation of the data is more sound, that being both true and valid. The time of a neutrino interaction was measured taking the earliest time detected and comparing it to the extraction signal and correcting for known timing delays. In other words, just slightly faster than light. Even more of a problem is that the neutrino is assumed to have mass, so not only is it forbidden from traveling faster than light, but even this guy knows that
The only objects that can travel at the speed of light are massless things like light.
Notice that in this equation, the deviation has a negative sign. This is not the same time of flight equation as is used by CERN, both in 2011 and 2012. Moving forward, turned out that, indeed, two systematical problems with the neutrino time of flight experiment needed correcting, upgrading a timing system and the Opera detector, in order to get an accurate measurement. The end results were synonymous with the Minos 2007 and Icarus 2012 results. Interestingly, other tests measuring the neutrino interactions using resonant plate chamber time measurements and target tracker data yielded subluminal results, traveling slightly less than the speed of light.
According to the official publication, the distribution using the target tracker data and the distribution using the resonant plate chamber time measurements are in agreement with the value obtained in the main analysis.
This is only possible through the overlapping of statistical error margins, similar to more than one umbrella covering a dry spot, though none of them happen to be directly over it. Though the desired answer is covered, so to speak, is it really being accounted for? If we really examine the data, the average mean is superluminal. All the data is slanted superluminal, with the exception of the new distribution using the TT and RPC data. Please take special notice that on page 28 it states that
every RPC plate provides an independent time measurement along with each muon track at a known position along the detector.
At a known position along the detector? This sounds like it's starting to bring up issues regarding the uncertainty principle, knowing both a particle's position and momentum. Could the apparent superluminal and subluminal data be accounted for in a more precise manner using a different mathematical interpretation regarding the dynamics of the nature of time? Are these distinct averages alluding to unaccounted for physical phenomena? If we look at the official publication data graphed on a probability chart, such as this, we can see that at some given probability for all of the data, that the main analysis is slightly superluminal. If the neutrino time of flight data was such that the neutrino traveled the speed of light or less, this curve would be more this direction, somewhere along here. What we have here is the main analysis data, and what we have over here was a new analysis done whereby the time of flight of the neutrino was slightly less than the speed of light. So when you take this data and this data into consideration, you see that the place where they overlap is pretty much in the margin of the statistical error, and even that is slightly to the superluminal side. So really and truly, the only justification for saying that the neutrino travels the speed of light is this area here where we barely have any overlap at all, and it's within the statistical margin of error of two different types of testing. We have a choice. We can either blanket this and put both of these datas together and sort of come out with an average mean between them both and say, okay, statistically the neutrino travels more or less the same speed of light even though it's slightly superluminal. Problem with that is the neutrino has mass, so how can we justify stating that the neutrino travels light speed? What seems to be a better solution to this problem is to apply the Existics equations. What we get is more or less a prediction of this same distribution of time of flights relative to the main analysis and these two new analysis. And what we can do is go ahead and plot out the figures to see where this more or less diagram comes from, representing 3 dimensions of time, and how this accounts for this curve. In the Existics equations, we replace basic ratios such as a over b equaling n, where a is greater than b. These ratios are replaced with a continued fraction such as this, if you look at the equation that's already in the CERN publication, this particular type of ratio is very similar to what in Existics we would use as the n or n star value. So we're going to go ahead and just apply the value that they get in the CERN data to the Existics equations, whereby this equals n star, and then the inverse of that would equal u star. Using the ratio we find in the CERN data regarding the speed of light compared to the neutrino speed, we can use it in one of two ways with the Existics equations. We can use it in the superluminal manner, whereby the neutrino is traveling basically a fraction faster than the speed of light, or where the neutrino is traveling a fraction slightly less than the speed of light. Here we have the Existics equations to find where the faster relative frame of reference, where they are slightly into the future relative to the person or thing in the slower frame of reference, and here's the equation to find the slower frame of reference is relative to the one in the faster frame of reference. The neutrino relative to CERN is slightly into the future, and that the neutrino relative to, say, the muon interactions is slightly into the past. This data here corresponds with the average mean of the main analysis, which was superluminal by about 6.5 nanoseconds. And this data here represents the lower margin of the new analysis, which was more or less subluminal. What I have here are 3 dimensions of time with CERN Gran Sasso and the neutrino plotted in the three dimensions of time. Here we have passage, the vertical component of time, associated with faster and faster or slower rates of the passage of time. Here we have the present component. You could think of it as sticking out of the chalkboard, sort of the present moment. And then we have along here, period, more or less what we tend to think of as linear time. So linear time, present moment, and the rate of the passage of time. These represent three different timelines, three different periods, each at a different passage of the rate of time. And as we can see, in this period the neutrino is slightly into the future relative to this neutrino, and this neutrino is slightly into the past relative to this neutrino. The neutrino relative to the neutrino, because it's moving at relativistic speeds, is experiencing the passage of time slower than CERN. And CERN would be experiencing the passage of time slightly faster than the neutrino. So what happens is, and what is not accounted for in general and special relativity, is that this neutrino is going to descend in the dimension of the passage of time down to a slower rate of the passage of time, and be the one that hits this detector. Therefore, it cross-cancels out the probability of this neutrino coming here, and so that neutrino goes down, and then this one up here comes down and arrives here. So this becomes the neutrino relative, I'm going to use this color, this becomes the neutrino relative to CERN. So notice that the neutrino relative to CERN is slightly into the future than the neutrino relative to the neutrino. So it, coming from a faster passage of the rate of time, arrives at CERN early. So what we can go ahead and do is map out that graph that we continue to see when we apply the Existics Equations in three dimensions of time. And so what we have is, here's the neutrino relative to itself, and here's the neutrino relative to CERN, and then here's the neutrino relative to light. So the neutrino relative to light travels slightly slower than the speed of light, and the neutrino relative to CERN was measured traveling slightly faster than light, because general and special relativity don't take into account three dimensions of time. And because of such, their data makes it appear that the neutrino travels faster than light, when in fact it doesn't. What I can do is I can draw right here the vertical component, which is passage, and then the horizontal component, remember, is period. And so what we have is that the neutrino relative to CERN is in a faster frame of reference than the neutrino relative to itself, given that the neutrino is traveling at relativistic speeds. So by applying this present and passage, so that we have three components of time, to this data, what we end up with is an explanation for why the neutrino would appear to be moving superluminal when it isn't. So the neutrino relative to itself is actually traveling slower than the speed of light, consistent with this data, and the neutrino relative to CERN, if you will, is traveling slightly faster than light relative to this frame of reference. So this extra aspect to relative frames of reference taken into consideration in existics, which you will not find in special or general relativity, appears to account for the data that we find, which more or less appears to be superluminal or subluminal, when in fact it's neither and both. The modern concept of inertial frames needs a slight modification, incorporating 3 dimensions of time into the conventional model.
The essential achievement of Existics, namely replacing the Newtonian inertial frame of reference with a more Leibnizian model of reference frames and applying it to relativity, is to overcome the rigidity of one-dimensional time using 3 dimensions of time, this being a directly relevant element to be added to the displacement field.
The official conclusion regarding the conventional interpretation of the neutrino time-of-flight data in comparison with light is that
the neutrino arrival time is compatible with errors to the one computed by assuming the speed of light in a vacuum. Of the new measured events retained, the average distribution is in agreement with the value obtained with the main analysis.
Rather than using statistical margins of error to blanket these anomalies, 3 dimensions of time allows for extra coordinates to be used without modifying the existing degrees of freedom already associated with 3 dimensions of space and other physical parameters. Instead of being elements of marginal error, these anomalies indicate a more fine and complex nature to space-time. Rather than having no meaning, these anomalies point towards the next level of physics, temporal dynamics, and how it relates to both relativity and quantum mechanics. Applying the Existics Equations to the neutrino time-of-flight data in comparison with the speed of light, it becomes apparent that the extra aspect of relative frames of reference missing from relativity and found in Existics can account for why the neutrino appears to be both slightly superluminal and slightly subluminal simultaneously, depending on how it is measured.